Okay, so today's lesson is on power, okay, and power dissipation in a circuit. So the first thing we need to talk about is we need to remind ourselves as to what power is and how that applies to electricity. Power is not in joules, but joules is a part of what power is. Does anyone remember what unit power is measured in? Watts. Yeah, second time is a charm. That's right. Let's get rid of this thing. Okay, so who can remind me of what the unit of watts is? Correct. It's joules per second. So basically, it's the rate at which power is being used. Or sorry, it's the rate at which energy is being used. Power is the rate at which energy is used. I guess a similar non-SI unit would be something like horsepower. Okay, it's essentially how fast energy is being used up. So if we look at the units here, we see some stuff that also is at play in electricity, right? So potential, electric potential is measured in volts. And what's the unit for volts? Joules per coulomb. And we also have current, which is measured in amps, right? Which is, remember, current is how fast pieces of electricity or chunks of electricity are moving through a circuit. Coulombs per second. There you go. Coulombs per second. If you take a look, we see joules, we see seconds, and we see coulombs, and we see coulombs to the power of -1. So if we were to take these two units, B times I, what we should end up with, once we do that, is the units for power. Okay, so we multiply coulombs to the power of -1 times coulombs. They will cancel off, and our remaining units will be in terms of joules per second, which is equal to watts. When we were learning about watts, I think we talked about where that unit came from and who Watt was. Just in case you don't, he basically was an engineer, I think, or some sort of scientist with an interest in mechanics and energy and so on. And he created an improved steam engine that was very successful, and it made him a very rich man. And for the work and stuff that he did in this area, they named a unit after him. All right. So I look forward to someday getting to teach about, the Sykes, right, or the Trites. What would the Sykes be a unit of? It's like style. Okay, so a new definition here then that we can use is P, power, is equal to current times voltage. So the power in a circuit, or the power, I guess the power dissipated by a resistor, is probably the best way to say it, is the current going through it multiplied by the voltage. Okay? There's a few more complex formulas you can make, because we also know resistance can be made equivalent to these units. So you can make some modified formulas from that. However, at this time of the year, I'm not going to get into bothering teaching you that. If you continue in electricity studies in the future, you will learn those formulas, but you can probably figure them out on your own. If you remember what, say, for instance, I is equal to from Ohm's law, and you replace that I here. Okay? So let's do a little, well, we'll write a note and then we'll do a little example, okay? So power, in terms of electricity anyway, power is the rate at which a resistor dissipates energy. And I think the easiest type of resistor to think about is just something like the filament in a light bulb or the heating element in a stove, right? Those things are just resistors that, as electricity passes through them, they turn the energy directly into heat, okay? So, you know, if you have a little circuit that looks, say, something like this, maybe not the best way to draw it, but say we have a little heating coil or a light bulb element, okay? And we have energy passing through it. Let's make this 6 volts, and let's make this a resistance of 3 ohms, okay? And I could ask you a question like, find the power of the bulb. And I think I can, no, it's not what I want to do. That's a great feature. The extend page feature, I really like that. That's much better than what I was doing before. Thanks, Brad. That's a Brad call. BVA. Okay, so so the first thing we have to do then is we got to figure out current. So before we can do power, we got to find current. Well, that's technically not true, but with the formulas we have, we do have to do that. Uh-oh, what happened to my pen? Yeah, pen. I wonder if there's a way to do this quickly. Back to pen mode anyway. Okay. So find current. This is a simple circuit. We know this. So if we want I over R, we should get 2 amps flowing there. Okay? Once we know that, right, and we have voltage, we should be able to figure out then that power, since it's equal to I times V, 2 amps, 6 volts, should equal 12 watts. Okay? So you're asked to find power of a resistor need current and voltage drop. Does that make sense? Do we need to try any more? Do you guys want to try one more practice? Okay. So I'll draw one more kind of complex circuit here, and we'll find the voltage drop across, the current through, and the power dissipated in a few different resistors. Oops, I don't like that. No. Whoops. Whoopsies. Well, it's a learning process here, right? Okay, so there's a bit of a circuit, and I think what we should do is we should deconstruct it down to its equivalent resistance and then work back up. Okay, so what should I do first here, do you think? What would be my first step? What's that? What about this guy, though? Add who together? Add 4 and 5, I agree. That would be the first thing, right? So if this becomes 9, 9 is in parallel with 3, right? Correct? So then we can find that, and then all of those are in series together, okay? So the 2 and the 1 are in series with this section over here. So yeah, so step 1 should be to sort that out. So there's a way to draw straight lines in here too, so my circuits don't look so... No, that doesn't work. Okay, so there's step 1. Then this section, right? Oh, I forgot the 1 ohm. Put him in over here. This section is now in parallel with itself, or with each other. Sorry, the 3 and the 9 are in parallel with each other. So we'll find that. Just do some calculator work. So that should work out to be 2.25 ohms. Okay? Of course. Good. So the next step is to redraw it. Our new understanding. Okay. Next step. All right, this now acts as just a series circuit. So 2 plus 2.25 plus 1, 5.25. Okay. That should do it. This is 24 volts. We can find the total current in the system using that info. Okay. Are you guys with me on that? Are you keeping up? Okay, I'll give you a second to catch up if you haven't. So let's roll back. We now know there's 4.8 amps leaving the battery and returning to the battery. So if we look here, that allows us to solve for 2 of our resistors' currents. 4.8 amps has to flow through here, because there's only one path through it, and 4.8 amps has to flow back into the circuit. After that, however, the 4.8 splits with some going this way and some going this way. Which way will the larger amount of current travel here, do you think? What's that? To the okay, yeah, to the right, through the 3 ohm resistor, right? Correct. The current over here experiences a resistance of 9 ohms versus 3 ohms over here. So we expect a larger amount of the current to travel through here. So we got to figure out what that would be. So what we'll do is we understand that this is a parallel part of the circuit over here. So you're going to have the same voltage across the 3 and the 9. We just have to figure out what that is, okay? How are we going to do that, though? How do we go about... So in the past, this is a kind of a new one, right? Because what we've done is we've added another 1 ohm resistor after the parallel part, okay? And we know the current traveling through the 1 ohm and the 2 ohm has to be 4.8, right? It's the same current. It's not a different current. It's the same current running around this circuit continuously. But how are we going to sort out what the voltage drop across this section must be? How are we going to go about doing that, do you think? What do we have to consider when we talk about that? Okay, what's the total voltage drop from this plate to this plate as the current travels through the circuit? Total voltage drop is 24 volts, right? So 24 volts, there's going to be a voltage drop here, here, and also here. So do we have enough information to work our way back and figure out what the voltage drop must be across this parallel plate part? Okay, Brad, how would we do that? We would have to find the what here and the what here. Speak up, guys. Okay, and Dylan, exactly what would we do to sort that out? How do we find the voltage drop here? Whose law would we use? Good. So we need to find the voltage drop across the 2 ohm, and we have enough information because we know there's 4.8 amps. And we know that it's 2 ohms. So 9.6, I believe. Is that good mental math or bad mental math? Okay, good. And this one's easy because the current is just multiplied by 1. Okay, so the voltage drop here is 9.6, and the voltage drop here is 4.8. So that should be 4 and a 1. So I believe 14.4 volts gets used between these two. So what remains must be the voltage drop across this part of the circuit. Are you with me? Does everyone agree with that? Is this math right? I hope so. Okay, so 24 minus 14.4 should be 9.6 volts. Okay, so 9.6 volts then represents the amount of voltage drop across the rest of this branch. Okay, so now we know the voltage drop here, and we also know the resistance here. So that should allow us to solve the current through this 3 ohm resistor, right? So we know that I is equal to V over R. So I is equal to V over R. On your piece of paper, it's probably very beneficial to make a little table and just fill these things in as you go. I'm kind of doing it like all over the place because I don't really have I guess I could have made a table and I could keep scrolling back to it, but just the way this thing works is probably not that practical to do that. So on your own paper, make a little grid that you're just filling these things in as you go, just to keep yourself organized. Like, you can do all your math wherever, but as you solve for a resistor, pop in its values, okay? I'll show you what I mean here. So all I mean is just make a, if I have a 1, a 2, 3, and a 4 ohm resistor or whatever it is that we have, just make yourself a little grid that has voltage drop, current through. Remember, the last thing we're now going to be able to figure out is how, why did it do that? and power. So you have a little grid. You just fill it in as you go. That's the easiest way to do it. Okay, back to where we were. So we've got 9.6 volts across this situation. So I get 3.2 amps coming through here, through this branch. Oh, you see, the one thing that I liked about that other one is if you press lighter, it makes like a thinner line, whereas this one's just always the same. Maybe I can turn that feature on. Here, I'll draw it over here. So 3.2 amps is coming through this branch, okay? So now we have to do some detective work because we know there's a 9.6 volt drop over here, right? So what we can do then is we can figure out the current that must be traveling through here, and there's two ways to do that, and I'll ask you what those are in just a second. Once we have the current, right, we then have the resistance, we can find the voltage drops in each. I don't think maybe I'll continue going through that because I think you can kind of do that on your own. But let's just look at the two ways we can sort out how much current is going, you know, through this branch. What's the first way we could do that? Find out how much current is going through this. Yeah. Good. So 4.8 was coming to this corner. 3.2 of the 4.8 went this way. So that leaves how much to continue along the way? So 1.6 amps is going this way. What's the other way I could sort that out? If I forgot to do, whatever, I didn't remember to do it that way. What's my other information I could use? Could I not just use 9.6 volts across a 9 ohm resistor? Is that going to work? Does that give us the right math? Hope it does.
Mr. Johnson?
Hello.
Are we still trying to phone somebody?
No.
Okay, thanks.
That's interesting. I get 1.06. I wonder why that is. Wonder why that would be. Should work. Must have made a math error somewhere, a minor math error. Well, I'm not sure exactly where I made a minor math error. Because we think we should get 1.6, but my math here, 9.6 divided by 9 gives you 1.06. So I'm not sure exactly where I went wrong. Anybody else getting those numbers? Yeah. You guys got the answer for where I went wrong? Yeah, here. Yeah. Okay. That could be our problem. Yeah, 4.6. Okay, that was the issue. That must be the issue. So, okay, well, if you make a mistake like that, everything is going to be slightly off continuing on. So this one probably won't make the list of online videos. But the point is, I'm not going to go back and redo it all because everything I did is legitimate besides I typed something wrong in my calculator. Okay? So this is why you would totally get carried through error on something like this. I would look at what you did and you'd just be just slightly out on everything. If this is worth like say 6 marks, you'd probably get 5 still because it's clearly just fat fingers, right? Which I'm often guilty of. So anyway, once you have the voltage drop in and you have the current through all of your resistors, then you just go P equals I times B for all of them, and that's the power dissipated by them. And then you're done, okay? And all the powers in each of the individual resistors should add up to the total power of the circuit, okay? And that's that. And that's grade 12 physics.